Alright, this is going to be our first introduction to chemical bonding, and we'll talk about covalent bonding, ionic bonding, and a little bit about metallic bonding. So there's a relatively small number of elements. 118 have been discovered at the recording of this video. However, elements can be combined to make an almost limitless number of compounds. Now, an important thing to remember is that the properties of the compounds are generally completely different from the properties of the constituent elements. So one of the examples I always like to use when I talk about compounds having different properties of their constituent elements is sodium chloride. So we know sodium chloride better as table salt, and table salt makes everything taste better. French fries, chocolate, you name it, you put a little bit of salt in it and it's going to taste better. But the properties of sodium chloride are very different than the properties of its constituent elements, sodium and chlorine. Sodium chloride is, of course, a white solid. Sodium metal is a silver shiny metal. It's incredibly reactive, right? When we put sodium chloride in water, it dissolves. When we put sodium metal in water, it bursts into flames. So you would not want to eat sodium because when it touched the moisture on your tongue, it would burst into flames and it would be incredibly unpleasant, right? Chlorine is a gas at room temperature. We also wouldn't want to eat chlorine. It was one of the first compounds used in chemical warfare during World War I, right? So a really reactive metal, a really reactive nonmetal, you would certainly not want to eat them, but when you combine them together into a compound, sodium chloride, you have something now that's much more stable and that is incredibly common in cooking and eating, right? But that is almost sort of the point. Part of the reason that elements form compounds, if we want to give them a reason, is because the compounds that they form are often more stable than the elements that make them up. Not always true, but especially for compounds that we find in nature, like sodium chloride, that is very often the case. So, compounds are made of atoms that are held together by chemical bonds, right? And these chemical bonds are just forces of attraction between the atoms. And all of chemical bonding basically comes down to Coulombic attractions. And that's just a fancy way of saying positive and negative charges attract one another, right? So two positive charges repel each other, two negative charges repel each other, but positive and negative charges attract. And so all of those different attractions and repulsions, that's what governs chemical bonding at its core. And so we're really looking at the attraction between protons and electrons, and then repulsion between electrons and protons when we're thinking about chemical bonding. So the three major types of chemical bonding that forms compounds are ionic, covalent, and metallic. And the first two, ionic and covalent, are the ones that we'll talk the most about. So for these different types of bonding, it's important to know what's happening to the electrons. It's important to know what types of elements tend to form these types of bonds. And so ionic bonds are typically formed between metals and nonmetals. And they involve the transfer of electrons. As we'll talk about, we know that metals tend to like to lose electrons, nonmetals tend to like to gain electrons, and so the electrons are transferred from the metals to the nonmetals. That then creates positive and negative ions, and those positive and negative ions want to stick together. So ionic bonds, metals and nonmetals, tend to involve the transfer of electrons. For covalent bonds, they tend to be formed between nonmetal atoms and other nonmetal atoms. And we know that nonmetals tend to want more electrons. And so, in some sense, neither one of them is willing to give up their electrons. And so they compromise by sharing the electrons. That allows them to both get more electrons. And my last slide is on metallic bonding. We'll talk about what the electron C model is in terms of metallic bonding. All right, I have my slides in a different order than we did on the previous one. I'm going to talk about covalent bonds first. So covalent bonds result when two atoms share some of their electrons. And this is generally found when two nonmetal atoms are bonded together. And not only is a covalent bond the sharing of electrons, it's more specifically the sharing of exactly two electrons between an atom. So a covalent bond is a sharing of two electrons between two different atoms. But atoms can share more than just two electrons. if they share just one pair of electrons, like all of the atoms do in a propane molecule, we would call that a single bond. So when I draw just a single line between two atoms, I'm drawing a covalent bond, and I'm telling you that this carbon and this hydrogen are sharing two electrons, and this carbon and this hydrogen are sharing two electrons. An example of sharing more than two electrons, if I was to draw the structural formula of an oxygen molecule, an O2 molecule, I would draw it like that, and I've drawn two lines. We would call this a double bond. So oxygen, or these two oxygen atoms in O2, are sharing four electrons. Each one of these lines represents a covalent bond, and each line represents the sharing of two electrons. In the case of nitrogen, a nitrogen molecule, I would draw three lines. We'd call that a triple bond. Those nitrogen atoms are sharing six electrons. And so the molecule, or the smallest unit of a covalent compound is a molecule. And when we write the molecular formula, it tells me exactly how many atoms are connected to one another in the molecule. An important thing to notice, I often talk about covalent compounds. Depending on your textbook, I think our textbook tends to use the term molecular compound more frequently, but these are really synonyms for each other. A covalent compound or covalent molecule is the same thing as a molecular compound, or a molecular compound. I guess another important thing, as we'll see when we talk about ionic bonds, these lines that I'm drawing here represent covalent bonds where I'm sharing two electrons. And so we would never do that when drawing an ionic compound. And so if you see us drawing these lines like this, that's a dead giveaway that this is a molecular or covalent compound. So ionic bonds result when we have electrons being transferred between atoms. And when electrons are transferred, the atom that lost electrons becomes positive, the element that gained electrons becomes negative, and we know that opposite charges attract one another, and so those resulting ions want to stick together. And so ionic bonds generally form when the metals are losing the electrons to become the positive cations, and the nonmetals are gaining those electrons to become the negative anions. Now, we don't have molecules in ionic compounds. No molecules, right? If I was able to blow up a salt crystal, what I would see is just an alternating array of the negative anions and the positive cations. And so if I look at this chlorine ion, for example, I can't tell which one of these purple sodiums it's attached to, and that's because it's not attached to any specific one of those. All of the negative ions are attracted to all of the positive ions. And so there aren't directional bonds like we have in covalent bonds. I can't say which two atoms are connected by the bond. All of the negatives are attracted to all of the positives. And so we don't talk about molecules in ionic compounds. Instead, what we might talk about are formula units. And so when we give the formula for an ionic compound, like sodium chloride, we're just giving the ratio of the ions that appear in what we call the crystal lattice of that ionic compound. And so in the case of sodium chloride, for every one sodium, there is one chlorine atom. If we look at another example of an ionic compound, calcium chloride, its chemical formula would be CaCl2, and that just tells me, right, there aren't CaCl2 molecules present. All the formula for an ionic compound tells me is that for every one calcium, there are two chlorines. So an important feature of ionic compounds is while they're composed of charged ions, the ionic compound overall has a charge of 0. So it's composed of individual ions, but overall the ionic compound is neutral. And so the ions have to combine in very specific ratios based on their charges. And so we'll talk about this a lot more when we do nomenclature, but I wanted to at least do a couple examples here. If I wanted to write the formula for the ionic compound formed between calcium and bromine, I would need to know their charges of those ions. Now, calcium and bromine, as we talked about in the periodic table video, these atoms, I can predict what their charges are going to be. Because calcium is an alkaline earth metal, I know that calcium ions, when calcium forms an ion, are going to be +2. And bromine being a halogen, I know that it's going to form a -1 ion. And so in order for this ionic compound between calcium and bromine to be neutral, because calcium has a higher charge than the bromine, I need more bromines to cancel out the calcium. And so the ratio that will give me a neutral calcium bromide would be CaBr2. If we do the same thing for aluminum and oxygen, aluminum is another metal where I know what charge it will have when it forms an ion. Aluminum is going to be +3. Oxygen is going to be -2. And so there's sort of two ways to figure out what the formula is in these more difficult examples. One is to sort of doing it kind of like you do a lowest common denominator. What's the lowest common denominator between 2 and 3? Well, that would be 6. So what do I do to get a +6 for aluminum and a -6 for oxygen in order for these to cancel out? Well, I'd need 2 aluminums and 3 oxygens, right? 2 times +3 is +6. 3 times -2 is -6. So when I add the +6 to the -6, Al2O3 will be neutral. And that's the way I like to do it. Another trick, and it really is just a trick. There's nothing actual about this, but one way to help remember, if you take the charge on one, it becomes the subscript on the other one. So the 2 from the charge in the oxygen becomes the subscript, the number of aluminums, and then the charge on aluminum becomes how many oxygens I need. But we have to be careful. If we can simplify these, we should, because for ionic compounds, we always have the empirical formula, and so it should always be the smallest whole number ratio. But we'll do more of this when we talk about nomenclature. Okay, the last thing, I wanted to mention metallic bonding just a little bit. So this tends to form when we have pure elemental metals or when we have alloys, so we have mixtures of metals. So they're sharing electrons in metallic bonding, but it's different from typical covalent bonds. It's sort of communal sharing of the electrons between all the metal cations, right? So we know that metals tend to like to lose electrons, and so they don't want to gain electrons, and so sort of nobody picks them up. And so we know that, so this is group 1 metals. This is what the alkali metals might look like, right? They all want to look like noble gases, so they're all willing to give up 1 electron. And so what we end up with is we have all of these +1 ions left behind, and then we have all the electrons that they're willing to give up sort of floating around, swimming around between all of the positive ions. And so it's very easy for these electrons to move around, and so that's why it's sometimes called the sea of electrons. It's like water molecules moving around these sort of pillars of the positive charges. If I was to look at an alkaline earth metal, right, they tend to form +2 ions, and so for each ion I sort of get 2 electrons. But again, these electrons are just sort of moving around. They're communally shared between all of the ions. But this allows us to explain many of the properties of metals. We know that they're good conductors of heat and electricity because in order to conduct electricity, we have to have electrons being able to move through the material. Well, because these electrons aren't really attached to anybody, they're free to move around when we apply a voltage to it, and so that makes metals very good conductors of electricity because of these electrons being communally shared between all of the atoms. Also, because we don't have the directionality that we do in covalent bonds, this sort of explains why metals are malleable and ductile, because we don't have, this atom isn't connected to this one like it would be in a covalent bond. They're free to move around.